Hey everyone. Alright, so we're going to look at um, finding an estimate for a mean if you don't know the population standard deviation. And so to do that, what we're going to look into are what are called t-tables or t-scores. And you're going to get me doing the one thing I don't do that often, which is jumping back to slides because of some drawing issues. So let me see if I can get the slides to pop up here. And I also want to make sure I can get a t-table up for you guys. Coming here. There we go. Okay. Trying to get Pearson to open up the textbook. There we go. And nope, still drawing a blank screen. That's what I get for having the electronic textbook. But let's come over here. There's our Excel. And what I want to do here, I want to try to get you to, there we go. And that's how I want it there. And just fit this on here so we can see our t-distributions. Sorry about this, and technology doesn't always get you what you want. There we go. That works out nicely. All right, and this is what we're going to talk about is the t-distribution. And still, Pearson is giving me a problem, but I'll have a table copy in there. And so what happens is we have been able to talk about estimating something of the population, which is what the mean is. We've been doing that using the sample mean and the standard error of the mean from the sample. But we knew what the population standard deviation was. It was a well-measured thing or something like that. But this isn't always known. And so if this isn't known, our way of doing estimates for the mean, well, we'll still use the sample mean. But what we're going to want to do now is use the sample standard deviation. And what that'll do is will give us not a normal distribution, but a t-distribution. And the t-distribution is interesting. So let me come over here. There we go. And switch us over to this. And we'll get a look at what the t-distribution looks like. And so we have a formula for the t-distribution. It looks like a z-score. Has all the same components except for the sample standard deviation here. And, well, let's look at the distributions this creates, and then I'll point out some properties of it. And so, t-distributions are a collection of curves. And the blue curve is your standard normal curve. And these curves underneath it are called the t-distribution. So here's the t-distribution with 2 degrees of freedom. Here's one with 5 degrees of freedom. The more degrees of freedom you have, the closer it comes to the normal curve. And so the degrees of freedom is the thing I think we're going to talk about and what it means. And what happens in this curve, it has the mean, median, and mode down the middle. It's symmetric. The area under the curve is 1. It's just not quite the normal curve. There's more stuff on the edges. And I'll just pull these up here and see if I can navigate through this one. There we go. The mean, median, and mode of the t-distribution are 0. It's bell-shaped and symmetric. Total area under the curve is 1, and it has that thickness to it. The standard deviation of the t-distribution varies. The more degrees of freedom you get, the smaller the standard deviation is. But it varies with the sample size. And to do that, we use this degrees of freedom, which are the number of free choices left after a sample statistic is calculated. You kind of need, since you don't know the standard deviation, you need one and another one to compare it to. And so the degrees of freedom are n minus 1. Your numbers of samples minus 1. What we can do is we can look up the values in a table, and a table in the book, which is why I was trying to load the book on the web page, and why I pulled this up was to see it. And so if we want a particular confidence value, 95%, we're going to say the sample size is 15. Well, if the sample size is 15, we have 14 degrees of freedom. So you come down to the side of the table under degrees of freedom, and you go to 14, and then you come down to the level of confidence being 95. And we see that our critical value for 14 degrees of freedom is 2.145, which, if you remember from the Z-score, it was 1.96 there. So this is a larger value coming across. But then everything else ends up being kind of sort of the same. We just have a different value that takes into account our uncertainty in the standard deviation. And it adjusts for it by having larger critical values. Let's come over here. And so let's look at what this t-value looks like. There we go. And so we have a 95. Whoops. There's my mean. And here's my negative 2.1545 and my positive 2.145. And I've got 2.5% of the data here and 2.5% of the data here, 95% in the middle. So it does the same job as the Z-score, or the Z-table did. And so what we want to do here is kind of the same thing that we did for confidence intervals for a mean if we don't know the standard deviation. So the first thing we say is, I don't know what that is. My sample size is greater than 30, or the population is normal. And of course, everything has to be random. So we go through our data, and what we need to know are the number of samples we took, the average, and we have to calculate the standard deviation of the sample, which in Excel was the straight out standard deviation. You could put a pop.s in it, but by default it does the sample. And if we remember our formulae for what they mean, not how we calculate them, there's my mean, and my sample standard deviation looked like the population standard deviation, except it had an n-1 in the bottom instead of n. And that's the difference. All right, well, once we have these, then we need to identify the degrees of freedom. So we go, hey, how many degrees of freedom do I have? Well, it's n-1. And we need to then set our confidence level. And our next step then is to find the margin of error. Right, so these are what we measure. Whoops, we set these. And our margin of error is going to be based off the critical value times the sample standard deviation divided by the number of samples. Now remember, knowing the confidence level and the degrees of freedom means you look up in the table and you get that critical value like we did before. And so the steps are the same, just the one piece of data changes. And so that's what's nice about it. So let's think about an experiment with this. I will use the confidence interval for the coffee shop in here. And yeah, there we go. So there are 16 coffee shops. And we go and we measure the temperature of the coffee in them. And we find out that the average of my samples is 162 degrees Fahrenheit. I go through and I calculate, and I find that my sample standard deviation is 10 degrees Fahrenheit. Now, I know nothing about what coffee would be like other than the sample I took. And so I want to construct a 95% confidence interval for this. Well, I have the data I need, and I have the idea that I want. What I want to do is I want to find the margin of error, which is going to be my t-score critical value, because I don't know what the population is like. And my t-score critical value times the population standard deviation square root n. I'm trying to remember now, and I need to look on my sheet here. Is it n or n minus? Yeah, it's square root n. I always get the n minus 1 added a little bit here. All right, and so this is what we want to construct. So we want to figure out the degrees of freedom. So that's n minus 1, or there are 15 degrees of freedom. Now we go to our table that we had previously. Let's see if I can get Pearson to bring this up here. Nope, still not getting the textbook on Pearson's website. Let's see if I can get it on here. Yes. Back here. Alright, so here I have part of the table which I wanted to see. And so I have 15 degrees of freedom and a confidence interval of 0.95. That means I use a 2.131 as my critical value. So we use 2.131 as my critical value. So now I can find my margin of error. Take 2.131. I'm going to multiply it by 10.0 degrees Fahrenheit divided by 16. Right, because that's my actual n in there. And my calculator is going to tell me that that's 5.3 degrees Fahrenheit. So that's my margin of error. My sample is still the estimator. And so I can say that the population average coffee temperature is going to be 162 degrees Fahrenheit plus or minus 5.3 degrees Fahrenheit. Or as your book likes to write it, let's see, 167.3 mu, and if I subtract the other way, 156.7. Because your book likes writing it in a range like that. And so we've constructed the confidence interval. Notice nothing is different from what we did before. There's nothing new here except these two things. We have to use a different table, a different critical value, and we have to use the sample standard deviation. Well, that means that our technology will also be slightly different. And what we want to do is use a confidence in a t-table. And let me bring it over here. And right now you're not seeing this other screen, are you? Okay. Let me try to move this over. Let me open up this here. Sorry about that. Alright, and so our technology can do this for us. So notice I can do a confidence.t. I give it my confidence level, which remember is 1 minus the 0.95. And then I need to give it the standard deviation of my sample now, and the number of samples I have. Now I'm going to show you something neat here. I'm going to go back to this data student athletes. All right, and I'm going to get a T confidence level for that. I'm going to do this whole thing saying, let's say I did not know the standard deviation, and I want to create my range here, my confidence value, just from this data. So the first thing is I have my mean, but now I actually want to get how many pieces of data I have here, because I don't always know what my B1 to B40. And so I can use the count function to count how many pieces of data I have. And this would be nice if I'm actually working on data and I don't know how much is there, it comes or it goes. So I can use the count function for this. And now I have everything I need to calculate my t-value confidence levels and put it in here. So what I'm going to do is I'm going to calculate my confidence value for a t-table. I'm going to be 95% confident. Right, so 1 minus 0.95. And then I need the standard deviation. Well, I can come back over here. Whoops. And I can calculate my sample standard deviation. And this is stuck for a second here. Let me de-stick it. So I want the standard deviation of my sample, which was B1 to B40. And I have it calculated now. So I come over here to do my T confidence, T, 0.95. And now I have a cell that this is in. So I'm just going to click on that cell, C3. And then my size, I'm going to click on this cell. And I now have a confidence interval based off of my data alone. And that's what the t-tables do for us. T-tables mean we don't need to know anything about the population, and it gives us a good confidence level of what we think the population is. So notice we haven't added much more, but we've created a way of dealing when we don't know anything about the population at all. And that's the difference between you're using your z-tables and your t-tables. What you know about your population versus what you don't know. And most of the times when you're doing statistics, you don't know anything about your population. So t-tables are your friends.